So we're going to create a complex piecewise function. Okay, so complex, we want to draw. Actually, we don't want to draw. Drawing means perfectly, right? So sketching means that you have to label it perfectly. So complete, complex piecewise functions. So let's say I got f of x is equal to x squared from x is greater than negative 5 up till it's equal to 2. Let's make it 0. And then it's an absolute value function, or even let's say a cubic function. Let's make it a straight line. Let's say it's 3x minus 1 from x is greater than 0 but less than or equal to 3. And then it follows an absolute value function. We could keep this one as an absolute value function and then it's all in one. So we've got cubic function, and let's try one other function like hyperbola. 3 over x from x is greater than 3, and that's it. All right. So it's going to start at negative 5 and go until infinity. Let's see if we can sketch this function. And how would we sketch this function? We need to get the domain starting at negative 5 and ending or having 3 in the picture at some point. Okay, so here we go. So this is sketched, right? Negative 1, negative 2, negative 3, negative 4, negative 5. That's my starting point. And I know I've got to have 1, 2, and 3 at some point where the graph is going to continue with that in mind. If I put negative 5 into this, negative 5 squared is 25. So let's apply 25 value over here. I can also see that this is a parabola, which is a smiley face. So maybe we need to analyze each function separately first. If I've got the x squared function, I can see it's a smiley face, and it's going to be turning at 0, 0. Because x minus p squared plus q was my parabola. PQ is my turning point, but it's 0. So my turning point is going to be 0, 0. And this function actually stops at 0, which means that it's going to be dragging along like that on a normal day, but we're not going to see that part. Okay, so we're going to remove that part from there. We want to give it as much accuracy as we can. If I put negative 1 in there, it must be 1. So let's provide a few values here. We could use a table method for each of these. Table method for each of these, and you're done. If I put negative 4 in there, it's going to be 16. Okay, so negative 4 gets me 16. And this is 25. So let's gauge 12 and a half will be here. So 10 would be, let's say, here. So 5, 5, 10, 15, 20, 25. That looks more or less equal. Just keep it blue. So it's going to be 5, 10, 15, 20, 25. This is negative 4. And I'm going to use a red line for this particular plotting process. Negative 5, 25. Negative 4 gets me 16. Negative 3 will get me 9. I can see properly. And negative 2 gets me 4. Negative 1 gets me 1. And 0 gets me 0. So that's more or less the trend that I want this to follow. Okay. It's excluding negative 5. So we're going to put an open circle at that side, and we're going to put a closed circle on this side. So it's ending at 0 with a closed circle. Then the absolute value function takes over. Let's analyze that one now. This absolute value function, which is, let's go at the top here, y equals the absolute value of 3x minus 1. We can see from here that if I take 3x minus 1 and make it equal to 0, x will equal 1 over 3. Which means if I put 1 over 3 in here, y will be 0. Okay, so that means 1 over 3 and 0, because remember this function here is plus 0, which means it's not actually going up or down, it's just going left or right. And in this case here, because x is equal to 1 over 3, it's going to go, in this case, since negative, right? So x equals 1 over 3 is going to be the point. This is 1. 1 over 3 is actually just there. And the line is going to be going this way, up, with a gradient of 3. It also go this way as well, right? It also goes this way as well. Okay. If I provide some of these x values in here, and maybe develop a table, maybe that will be even easier. So let's go x, y. Let's get a table going with 0, 1, 2, and 3. 0 goes in there, becomes negative 1, becomes positive 1. 1 goes into there, becomes 3 minus 1 is 2. 6 minus 1 is 5. 9 minus 1 is 8. And that's all we got to plot. 1, 2, 5, 8. So 1 is here. Yeah, x is 1. And then y is 2. X is 1 and y is higher, which is 2. All right. And then x is 2. Then it's 5. And 3. And then it's 8. So we can see that all of these are aiming at that point. Then what's happening is jumping up there just for a little bit. So we end up with a straight line going down to the point 1 over 3 and up this way. Okay, so where each of these points can just adjust it onto that line. Excluding 0, by the way, so we're going to put an open circle at 0. Open circle at 0 and closed circle at 3. But we don't need that. We've got to stop that. So that line there would be reduced down till there. All right. Next, hyperbola. Got our hyperbola. X is greater than 3. Let's provide some values in the form of a table here. The table method seems like the fastest at the moment. So we've got y equals to, let's put it at the bottom here, y equals to, wait in here, 3 over x. And I can see that if I put x equals to 3 first, it'll be 1. So y equals to 1 if x was 3. So let's give reasonable values for this because we're going to divide it. So if x is 3, y is 1. Because 3 divided by 3 is 1. So then let's go greater than 3. So let's try another factor of 3, maybe 6. Multiple of 3. That'll be half. If I go 9, it'll become a third. I could then go 12 to become a quarter. And it's getting closer and closer to 0. Okay. As this increases, it's going to get smaller and smaller, maybe. Let's have a look. The next thing we also note is that if we have a normal hyperbolic function 3 over in the form of its original x minus p plus q, p and q is going to be my asymptotes. So p equal to 0 and q equal to 0 in this particular, because it's plus 0, means that we have asymptotes on the x-axis and we have asymptotes on the y-axis. And we also know that 3 is positive, which means that the graph is going to end up in the top right-hand corner and the bottom left. So it's going to sort of do that. But we don't need that one. We only need this one. And we only need it from there onwards. So here we go. So we're going to go 3 and 1. So we can plot this one, 3 and 1, which is over here. And it's on there. It's right on there, right? Excluding. So it's actually got to be an open circle somehow, but it's actually continuing. Because this is continuing like that, this overrides it. Because it's just going to continue from a solid dot. So that's going to be my first dot. 3, 1, 6.5. So 1, 2, 3, 4, 5, 6, and a half, right? So 3 and 1, which is quite low. 6.5 is there, and then it gets really tiny after that. Actually, it's not actually meeting up at that point. It's actually meeting up here. It has to be an open circle. 4, 5, 6.5, which is there. And this line is going to be continuing this way, all the way down there. Let's just change it up a bit. And let's make this equation a bit more realistic. Let's say we got 3 over x, but we want to plus 4. We want to plus this. So if I make x equal to 3, I get 1 plus 5, which is going to get me 6. So let's start with that rather. X is 3. That makes more sense. So y will equal 6. And that would be 5. So 6 would be here. And it would be an open circle there. If let's choose another value, maybe just 6. And it will be a half, it will be 5.5. 5.5 is going to be like slightly lower than that at this point. Either way, the graph is going to be doing something like that, tending all the way down. Okay. But that one I can see and draw. Okay, so when we do this, we can see that the table method actually works out the fastest. But knowledge of the equations and knowledge of functions helps a lot, because I could tell that this hyperbola was only going to lie in this quadrant. And I knew that this parabola was a smiley face. So it gives me a sense of reassurance. And we must label our x's as well. So y and x there.